Okay, what is everything in the entire universe actually made of? I mean, really, it's one of the oldest questions we've ever asked, and the answer, well, it's a fantastic scientific detective story. So let's dive in and see if we can uncover the fundamental building blocks of all matter. Just take a look around you right now. Everything you see, the screen you're watching this on, the chair you might be sitting in, even you, it's all made of the same basic stuff. All these different materials are just unique arrangements of the exact same fundamental building blocks. But the big question is, what are those blocks? To start our investigation, we have to go way, way back in time, long before there were labs and experiments. You see, the first clue in this mystery wasn't actually found. It was imagined. Thousands of years ago, brilliant thinkers in totally different parts of the world had the same incredible idea. In ancient India, a philosopher named Maharishi Kannada theorized that if you keep dividing matter, you'll eventually hit a final, indivisible particle he called Paramanu. And all the way over in ancient Greece, Democritus posed a similar thought experiment, imagining a final, uncuttable piece of matter. So Democritus called his uncuttable particle atomos, and that's the word that ended up sticking around. It's the origin of our modern word atom. Now, for more than 2,000 years, this was just a philosophical idea, a concept. But then, science finally entered the picture. So how did this ancient philosophical idea turn into the first real scientific theory? Well, as it turns out, that theory was almost immediately shattered by a totally shocking discovery. In the early 1800s, a guy named John Dalton gave scientists their very first working model. He proposed that atoms were these tiny, solid, indestructible particles, kind of like microscopic billiard balls. It was a simple, really powerful idea, but it had one major flaw. So was the atomos really uncuttable? The answer, as it turned out, was a huge no. You see, the first clue that something was hiding inside the atom was just about to be revealed. And here is our first major plot twist. In the late 1800s, a physicist named J.J. Thomson discovered a particle that was smaller than an atom, the electron. This was absolutely monumental. It proved the atom could be divided, completely shattering that 2,000-year-old idea and forcing him to come up with a whole new model. A sphere of positive pudding with these little negative electrons scattered inside. Thomson's experiments showed that these new particles were negatively charged, and they were incredibly tiny. We're talking over 1,000 times smaller than even a hydrogen atom. And super, super light. This was the first subatomic particle ever discovered, and it basically opened the door to a whole new world inside the atom. And, why call it the plum pudding model? Well, because it looked a lot like a popular dessert in England at the time. You just have to imagine the cake part is the sphere of positive charge, and the raisins or the plums are the negative electrons, just kind of stuck in it. It was a tasty, but as we'll see, an ultimately incorrect picture of the atom. So the plum pudding model seemed pretty plausible. But one of Thomson's own students, a man named Ernest Rutherford, would design an experiment that would completely blow it out of the water. And this is where our detective story gets truly dramatic. Okay, so Rutherford decides to test this plum pudding model by shooting these tiny, positively charged things called alpha particles at a super, super thin sheet of gold foil. He totally expected them to just zip right through the soft pudding of the atoms. But what he saw was astonishing. Yeah, most did go straight through, but some were deflected, and a few, a tiny, tiny fraction, bounced right back at him. So this was the setup. A beam of alpha particles fired at a thin sheet of gold foil. Rutherford later said the results were as surprising as if you had fired a 15-inch cannon shell at a piece of tissue paper and it came back and hit you. Just, wow. This strange pattern of scattered particles, this was the crucial clue. This was the evidence that allowed Rutherford to figure out the true structure of the atom. His first conclusion? Because most of the alpha particles passed straight through, completely untouched, the atom couldn't be a solid pudding. It had to be mostly empty space. And what about those few particles that bounced back? Well, the only way to explain that was if they had hit something very small, very dense, and positively charged, something powerful enough to repel those incoming positive particles. Rutherford had just discovered the atomic nucleus. So, Rutherford's new model of a tiny, positive nucleus with electrons orbiting it was a huge leap forward. But, like with any good mystery, solving one puzzle just revealed another one. Right, so here was the new problem. When scientists calculated the mass of the nucleus based on the number of positive particles, the protons, The numbers just didn't add up. The nucleus was consistently about twice as heavy as it should be. Something else had to be in there. And the final piece of the puzzle was finally found in 1932 by James Chadwick. He discovered a third particle hiding in the nucleus, the neutron. It had no electrical charge at all, but its mass was almost identical to a proton's. This was the missing mass. And with the discovery of the neutron, all the main characters in our story were finally accounted for. We could now put together the complete picture of the atom. So here it is. A tiny, dense nucleus sits at the center, and it contains the positive protons and the neutral neutrons. Then you have the negative electrons orbiting that nucleus, and it's the simple electrostatic attraction between the positive nucleus and negative electrons that holds the entire atom together. What an incredible journey, right? We started with the simple, solid sphere of Dalton. Then we moved to the plum pudding of Thomson, and we finally arrived at Rutherford's nuclear model. This timeline shows so clearly how science actually works. Each model built upon and corrected the one that came before it. But even this solar system model wasn't the final chapter. Not even close. In fact, it raised brand new questions that led to an even stranger, more fascinating picture of reality, the quantum mechanical model. The key takeaway here is that the detective story never really ends. The deeper we look, the more mysteries we find.